Okay, good afternoon to everybody. I'm happy to hear and see you again. And today it's our lecture number 10. We unfortunately don't have tutorial today, but we will pick it up during the next weeks. We are still ahead of schedule because we didn't have any breaks this year, except for the previous week. And this lecture was the last lecture for the previous year, but I guess we might even pick up a bit more this year, which is good, right? You're gonna know more from us. So knowledge graphs. Knowledge graphs is quite a big area in social media computing, and this is a quite important area when it comes to combining humans and machine. So basically, it's all about making it useful what our data science and what is our AI technology can actually do for humans and help humans. Talk about motivation, applications. We'll talk a little bit of the knowledge graph history, and we'll talk about taxonomy, factual knowledge, and temporal knowledge. So we are all in a big data era, and data is really big. So data itself is not very useful. In order to make it be really useful, we need to generate the knowledge. And knowledge is not just data. Knowledge is like processed data, right? You have a question, you need to understand the question, and then you need to process it to receive the answer. And knowledge is a key to the interpretation and inference. So basically, it's a key to really figuring out what you should do. If you want, it's like a recommendation or question answering type of task for machine learning. Knowledge is a power, and if a program to perform a complex task, it must know a great deal about the world in which it operates, right? So that's what Lentz and Friedman have said in Artificial Intelligence 47 in 1991. If you generally want to talk about this, you might come across an application of this in a structured text. So for example, if you have a lot of text and you want to you want to be able to use it, right? You cannot just like have lots of text and like read everything, right? Then there wouldn't be much meaning, because there's no human that are really capable of doing so. So you want to be able to process that, and to process that you need to be able to process and transform this unstructured knowledge into structured knowledge. So basically bring structure into that. About 85% of all information is unstructured, and vast majority of CEOs, basically those people who direct the company, expressed a lot of frustration of their organizations and ability to glean insights from available data. And that was studied by IBM from 1.5k thousand of CEOs. And being a CEO of the company, I also understand what they mean, right? So having data is not enough. You need to be able to understand structure and make use of it. And this is the key here. So structures are useful for knowledge discovery. Structures can be built by humans when it comes to small company, maybe 10, 15 people, but it's too expensive to build this structured by humans for very big organizations. And honestly, there's a couple of startups that are really busy with this. If you look at a startup called Tiger, they're in Russian market. They have been created in Singapore, but they're also led by Russians. You'll see that the whole business of the company is about recognizing the digital documents, or doing optical character recognition, and then structuring this so that the people in the bank can really figure out what's going on, who is talking to who. And you can use many procedures. You can use clustering, you can use topic modeling to summarize and bring new knowledge, create new knowledge, figure out the stuff, right, and process the data. efficiently. There is a kind of information overload, and this is a critical problem in the big data era. So let's say in 2020, information will be doubled, and it's doubled every 73 days. So you can see that with the emergence of the internet around 2000, the information started growing like that, and that defines the era we are living in. So let's say if your parents or grandparents have been born in 50s, 60s, 70s, they, of course, it's difficult for them to adapt into our current situation, current structure. And unstructured or very loosely structured data are prevalent. Loosely structured data can be, for example, message with the hashtags. There is some structure. You can find this data by the hashtag, but the sentences are often structured. So this is loosely structured. So every year, hundreds of thousands of papers get published. Research papers, right? Something very formal, not even social media. So inside these papers, unstructured data is a paper text, and loosely structured entities can be authors, venues, keywords, categorization by the conference system. And every day we get more than 90K news articles produced, and content is unstructured data. And you can extract some entities from there, such as persons, such as locations, such as organizations, and that will be the structured data. Give me a moment. So example is the articles here, and then you can see this information. So then we can go to another example, which is social media. Every second, about 150,000 tweets are sent out, and unstructured content will be tweet content, right? So it's like unstructured data inside. And the loosely structured entities will be the Twitters, the hashtags, the URLs you are finding inside. So then these two content together form this loosely structured social media. You going further, you can also see that there are some social images and videos, and inside there you can see that this online videos also like visual data is unstructured, and some information such as likes, hashtags is structured data. I just noticed I was muted, so let me go through the previous slides again. So basically, this example is about news articles. This is example about social media, where the structured data is a content, and then loosely structured entities are Twitter's, hashtags, URLs, etc. So some text-attached information network can be built for unstructured and loosely structured data. So information network is basically text plus linked entities, and then is a pretty common way to organize this information. So what is entities? There is such a technology called named entity recognition, which is pretty much text classification problem. So if you have some text, for every word, you can basically predict whether it's an entity or not entity. And if it's entity, you can also predict the entity type. So for example, we have topic. For example, we have a venue. For example, we have an author, right? We can have organization, location, person, hashtag Twitter, URL, and many other things. And then if you go in further, you can also come up with a more comprehensive entities that are related to particular industry. So for example, we have this text, and then you can extract the entities inside this text, and you can build an entity graph, how they're related to each other, etc. So we can also have a structured database queries, therefore, and we can do some information network analysis, right? So it's very often when data get enriched by the named entities by structured, and then after that, you can have a queries in the database to make it much more organized, rather than just like doing pure search, or in image case, you can even do any search at all, right? So this is how it works. And you can see some framework, like for the image data processing. For example, if you have low-level vision, like basically like the image itself, if you feed it into the convolutional neural network, you can actually detect the objects inside there, right? So you can see there is two people, there is also some tree, there's a dog on the ground, etc. Right? So we can split this into different types of components of the image. Is a person talks to person? Is a clock above the person? There's a car with a wheel. There's a person telling a story. And then, of course, in a high-level language, you can actually explain this. That the man in the red is talking with the man in a gray in a street. But also, this can be further transformed into the question answering system, where you can ask what color in the jacket of the man under the clock, and then answer can be gray. Yeah, so this is typical multimedia question answering type of application. So what is the knowledge graphs, and why knowledge graphs are so important? We have lots of entities around us, and they are connected with some relationship. It's a graph, right? So we need to store them, and we want to use a database or a graph, or we can use an object databases, which is pretty much like a hierarchical graph structure, right? So it's not like relational database, but object database. No SQL database. So graphs can be processed efficiently and offer convenient abstractions, the way we used to work like a hierarchies. And then graph is a very natural that to represent the relation between entities, and therefore this is something you can work with. There's examples of knowledge graphs: Freebase, Yago, OpenIE, Facebook's entity graph, Wikipedia, Satori. Well, all big guys have created their own knowledge graph. So there are many applications of knowledge graphs. You can information retrieval applications. You can use it for natural language processing, database machine learning, artificial intelligence, and you can also use it for internet search, for connecting people and places. Social networks themselves, it's a bit like a knowledge graphs because we put lots of labels about ourselves, therefore the graph is enhanced by these relationships and attributes. We can do question answering, text analysis, and many other applications. We can do internet search on the Hurricane, and then we can see that National Hurricane Center, Hurricane Radio, Hurricanes, where the Hurricanes Festival. Then if you look in look at a Hurricane Singer inside a knowledge graph on Google, you can also find Bob Dylan. Right? So this is the way he was famous, because the band that he has organized was called Hurricane. And this kind of information can be only retrieved from knowledge graph. Otherwise, how does it you know that Bob Dylan have such a band organized, right? So so this is how the knowledge graph can work. It helps you basically to connect the entities that have several relationships one from another. Another example is New York population. If you search, you'll see 8.4 million in 2013, right? And then it allows you to see information about the New York itself. So you can see that inside the population is 8.4 million, right? So New York, the city population is entities that are close in the knowledge graph to each other, and then are very associated to each other. Therefore, they are commonly used to together to basically show the point of knowledge graph and all these things, right? So there's like a knowledge graph and entity related to each other that get assembled in one summary in the right side of Google. I have a question answering. So Barack Obama place of birth, Honolulu, right? So like Hawaii. Yeah, so you can also get that, right? So on Amazon, you have question answering. When you ask a question, they can answer you in a Siri Apple. This question even asked spoken in a natural language, and then Siri can reply. So this town is known as a Sin City. It's downtown is Glitter Gulch, right? So this is American city, has two airports named after a war hero and World War II battle. So a question classification is a one problem, and then you have knowledge backend that basically have this database to infer the knowledge, right? So the IBM Watson, as you can see, that it has bet the players of the game very, very well because they have a backup of the system, and then they also have the question recognition system, and then therefore they can do inference through the knowledge graph to do it much better than human for this popular TV show. So the question was Sin City, right? It's a movie, it's a graphical novel, a nickname for city, etc. And answer is Vegas Strip, right? So Vegas stars, but this is how does this inference has be done inside in the backend of this inference system. So knowledge graph have a history. It was defined by mathematical rules, logics, pretty much in '85. Then it was defined by WordNet. It's like what is belong to what. So WordNet should be very familiar to you because we have ImageNet, we have WordNet, and we were talking about it as sufficient data representation. So knowledge graphs are useful as ways to produce feature for our research and our systems as well. We get Wikipedia. There's a 4.5 million English articles and 20 million contributors. And then since 2005, then 2010, and now we have those modern knowledge graphs such as Yago, Wikipedia, and Freebase. And then we get even more advanced, both from alpha and all, etc. So knowledge graphs was created for humans and by humans in the past. So basically, it was human-created knowledge graphs, or maybe machine-assisted, like Wikipedia, when it's a collaborative manner and everybody trying to create that together. And then, of course, we also have the knowledge graphs created by machines in the later stages. So web of data and knowledge is like a linked open data. Many knowledge graphs get put together, and this is a concept that has all the things put together. You can go for the link here in the bottom, and then you can choose this. So it has more than 60 bios, subject, predictive object triplets inside from more than 1,000 sources, right? So it's like very structured database that can be used by you as well. Then database, DBPD, and Freebase are inside. So it has more than 4 million entities in a DBpedia and more than 500 million facts and live updates. In a Freebase, we have 40 million entities, 1 billion facts, and core of Google Knowledge Graph, right? So basically, Freebase is what Google also uses nowadays. And we also have Yago that has 10 million entities, 350 classes, 100 million facts, 100 languages, and this is also the most accurate like mapping system at the moment, right? So if you want to find a trade-off between accuracy and size, probably Yago will be something you'll be looking at. And of course, we also have Google's knowledge graph, which is 600 million entities and 15,000 topics and more than 20 billion facts inside there. So it's like the biggest knowledge graph we have at the moment. So the representation inside might look like this, right? So you can have Yumin Zhang is a type of movie director, has like a taxonomic flow. We also have a factors knowledge, different categorization knowledge types, right? And Chang is directed by Flowers of War. As temporal knowledge, Yan Zhang is a member of Beijing Film Academy, valid during 1978, and it is temporal knowledge. Emergent knowledge, basically, Yun Chang was a classmate of K.H. Chen, and terminological knowledge, Lin Zhong is known as China's most beautiful actress, right? So this is different types of knowledge can be inside the knowledge graph, and there are some publicly available knowledge graphs that you can actually work with and incorporate in your final projects or inside your research. Um, Pragmatic definition of knowledge graph can be that this a very well comprehensive and semantically organized machine-readable collection of data. Relevant data is very, and this data is usually also domain-specific in terms of entities, classes, and facts, like some attributes and relationships and types of relationships we just said before, plus some spatial data, plus some common sense properties and rules, context and entities, facts, and many other things depending on particular knowledge graph. Knowledge graph also can be defined as structured and detailed information about the topic, in addition to a list of links to other sites. And the goal is that users would be able to use information to resolve their query without having to navigate to other sites. Basically, the main point of knowledge graph is be able to answer the questions and resolve the queries of the users. Let's take a quick break, and then we go for the next few parts of this lecture. Okay, so let's talk about how does the system work to build these knowledge graphs. So let's talk about taxonomic knowledge first, right? So taxonomic knowledge have entities and classes, scope and goal, or maybe some Wikipedia-centric methods are usually applicable for this type of knowledge graph construction. So this is like a label graph example of taxonomic person. So Elvis Presley was born in Tupelo. His type is relationship type is a singer. Singer is a person, and person is subclass of resource, and location is also subclass of resource. So therefore, resource is a kind of really very high level category on top. And at the same time, Tupelo is a city, and city is subclass of location, and location is subclass of resource, right? Knowledge base can be seen as a directed labeled multigraph where the nodes are entities and the edges are relations. So basically how it works. So we have classes, concepts, and types. We also have relations and predictions. Okay, I'm sorry, I got some background. Working from home, sorry, let me settle that. Okay, let's continue. I guess now background disappeared. So, and then we also have instances and linked with these entities. So entities can have different types of labels. So, for example, entity Elvis can have a label Elvis, right? So it's Elvis Presley have label Elvis, and it also have a type singer, and the singer is a person. But also Elvis can have a label the king, right? Because you know that Elvis Presley was also called the king of rock and roll, right? So this is another label, one entity but two labels. And at the same time, you can have some other artist who also called Elvis, right? He's doing a parodies on Elvis Presley songs, but this second artist has never get any additional label as the king, right? So you can see that this is the second singer on the right side. He is also Elvis, but he's not the king. And you can see that the same label for two entities, and there's some ambiguity happening inside, right? So if you will be going further, we can see that different ways as a knowledge base, right? So we have a graph notation, we have Elvis. Elvis have born in Tupelo, and Elvis is also a type of a singer. And this triplet notation can be stored in pretty much a database. So to store the knowledge graph, right? So you can see that Elvis is a singer, Elvis born in Tupelo. And you can also have a logical notation, like a type Elvis singer and born in Elvis Tupelo. I guess you have had these somewhere in your bachelor courses when we were talking about knowledge graphs, and when your lecturer was also talking about knowledge base. So probably this notation is quite familiar to you. The question is how to build it automatically, right? And that's we're gonna talk a little bit later. So our goal is finding classes and instances, right? So basically which classes exist, entity types, unary predicates, and concepts, and which sub-options hold, so subsumptions hold, right? Basically what is subsumption is under which entity, and also we need to figure out which entity belongs to which class, and we also want to figure out which entities exist to the end, right? So what are the set of entities we have for this knowledge graph, for this knowledge base. WordNet is a lexical knowledge base, and it was created in 1985, right? It's like quite an old project. So WordNet has 82,000 classes, and WordNet also have thousands of subclasses of relationships. So it's already a very powerful taxonomy, and I think one of the biggest advantages of WordNet is that it was created by humans, right? And therefore, it's very useful because it's validated, created by humans. Um, so we can have person, individual, and soul, right? WordNet contains 118,000 class labels inside. But of course, at the same time, the disadvantage of WordNet will be that everything is object, and then they have different levels of hierarchy. So for a certain object, you have 10 more levels of hierarchy on top of it, but some other leaf object may only have 3, 5. So it's not a very structured system. And therefore, at the same level of hierarchy, you might have a very different level of object hidden there, something like, let's say, in level 3 of hierarchy of WordNet, you might get both something very abstract like person, but also at the same time something very specific like a particular breed of a dog, right? Just because hierarchy of animals is maybe shorter than hierarchy of humans. So this is a disadvantage, and this is, I guess, implication of the fact that it was built by humans. So this is how WordNet might look. So we have a singer, we have a direct hyponyms. I'm sorry again for the backgrounds. We have a direct hyponyms inside, right? So we have that there he's a singer, musician, instrumentalist. He's also performer, entertainer. That he's organism and a living thing, animate thing, and a whole unit and object. I'm so basically this is how does the whole hierarchy looks. And you can see that there's multiple levels of hierarchy, right? So there's an object, physical object, there's a whole unit, living thing, animate thing, organism, person, entertainer, performer, musician, and etc. So if you look at this hierarchy, it actually can be very useful for you for the situations when you want to organize your data and extract the features. So for example, you have lots of unstructured text, but also at the same time you want to maybe categorize this text into the features. So you can actually search for the word inside WordNet, and then you can go to the necessary level of abstraction to get a category. So instead of, let's say, having bag of words as your feature representation, you might have a WordNet category inside to handle this. I will have to do a technical break. I still need to handle my background. Very sorry for that. I'm sorry for that. I had to attend to the child today. We are working from home, so sorry for that. So this is a hierarchy of the WordNet, and that's how it works. So we have this many categories, and then these categories can be used to actually infer a category for your data representation. So you can infer knowledge, you can do question answering, but also you can figure out not what like a particular word mean, but rather what is a higher level category, and then you can use this list of categories as a data representation, which can be very useful. Machine learning models can be representing data much better. Yeah, so this is a subclasses also, right? So we have vocalist, vocalist, vocalizer, and then we can see the different classes of vocalists. You can have alto, baritone, bass, choral or castrol, and many other type of subclasses, right? So this already is very specific to a particular area. So we also have a has instance relationship, right? So you can see the instances that belong to particular singers. So basically, you can see all the singers inside. You can see the Bob Dylan inside there, right? So it's of course Michael Jackson, and of course there is Elvis Presley as a rock and roll. So we have only 32 singers, 4 guitarists, 5 scientists, 0 enterprises, and 2 entrepreneurs. So WordNet is lack of instances, and this is the reason is because WordNet was created a long time ago. First, there are many people haven't existed yet, but not famous yet. But also at the same time, of course, it's created by humans. There is biased, right? So we kind of need the knowledge bases, knowledge graphs that have many more instances to solve our state-of-the-art tasks, right? And we want to go beyond WordNet. It's one of our main goals. So it contains only few instances. It have only common US classes, and it contains only English labels. But let's say if you want to deal with other language, if you want to deal with more specific industries, then there's many more avenues of improvement for us. So we have a scope of goal, and we have some Wikipedia-centric methods. So look, Wikipedia is another database that have lots of instances because it's newer and people keep adding stuff inside Wikipedia as a new entities, right? So categories, Wikipedia's categories contain classes. Yeah, so you can see there's classes. And categories don't form a taxonomic hierarchy. So basically, it's a lot of entities, a lot of classes, but there's no taxonomy for Wikipedia. And this is considered to be disadvantage because it's very hard for you to traverse to what each particular thing is really mean. So idea is, okay, why don't we link these two together, WordNet classes and Wikipedia categories, to form a much more advanced knowledge hierarchy, knowledge base. And categories can be linked to WordNet in a several ways. So WordNet have this kind of named entities categorization, right? Single person, people, this, and Wikipedia also can be split. Like Wikipedia descriptions can be split in a noun group parsing, right? So we have a pre-modifier, we have a head, and we have a post-modifier. So basically, it's like this called non-group parsing. It's NLP techniques. Then once we see there's a people, we can also stream the people to person, and then person is pretty much already linkage to the WordNet categorization, right? So basically, as long as inside the Wikipedia description we can find the right category from WordNet, we can connect them together and have a much better hierarchy, much better linkage, and much bigger and comprehensive hierarchy. And you can do it with images too, because we have ImageNet that is based on WordNet, and then you can actually link Wikipedia to the image knowledge as well, right, or vice versa. So we have a Wikipedia, we have a WordNet, a person, subclass of organism, and then we can have this linked combinations like this example in the Yago with 200 classes and Okay, here we report 96% accuracy before we say 95, but anyway, it's about that, and it's very high, and it's very, very comprehensive, right? So it was released in 3W 0.7. We also have a wiki taxonomy of 105 links is 88% of accuracy. So we can actually construct a linked Wikipedia and WordNet by random walks. So we can construct a neighborhood around the source and target nodes. So basically, neighborhood is like what is immediately connected things. Then you can use contextual similarities and glossaries as H-weights. Or you can even use word embendings and compute the actual distances in a Euclidean space to build these edges. Then you can compute the personalized scores, and then we can rank candidate targets by their personalized scores, right? So basically, you can create these link connections, and then only establish those connections that are really high relevance, so high chance that this connection really exists. So you have driver, operator, or vehicle that's get connected to Formula 1 drivers, right? So this is a relation that is happening. And Formula 1 driver is definitely not device driver, like a driver for computer program, because you can see that the connection through motor racing and truck drivers to driver is high as compared to connection to computer driver. So basically, we have weights of scores combined together, and that is a combination give you high overall rate, and we think that it's more likely that drive, not the computer driver for the device. We actually have can have a factual knowledge. So factual knowledge have a relationship between entities in terms of scope and a goal. So it can be a given relationship, like have advisor is a relationship between two people. Graduated at is a relationship between person and university. Has won prize is a relationship between person and award. Born on is a relationship between person and date. And fine instance of these relationships has advisors Jim Gray, Hector Grant, and head advisor Susan Davis, and graduated as Jim Gray from Berkeley. So it's something like what I was showing you before. We also can have one prize and born on, like different types of relationship depending on the industry. So information abstraction can be built upon the semi-structured data in a free text. So semi-structured data is like easy, low-hanging fruit, right? So we have Wikipedia info boxes and categories and HTML lists and tables. There's like a semi-structured data, or and then we have also free text where we need to cherry pick, basically figure out that particular case that can be used to link one database with another. So like before an example, there was a phrase from Wikipedia, and inside the phrase we pick up one word and then we link it to the WordNet. So that was a cherry picking. But we also can have one hierarchy, another hierarchy, and we just need to combine them together. That would be semi-structured data linkage. So for semi-structured data linkage, we get a good accuracy. For free text, of course, we get much poorer accuracy because we can have more places we can make mistake when we cherry pick the particular keyword, and then also we can have a problem in linking this keyword to another one to combine the data. So we also have the web tables, right? So basically, it's another type of data we can get. We can also extract regex based on the regex, right, regular expressions. So there is a data in info boxes inside the Wikipedia, so it's pretty much like a structured data. If you look into how it gets defined in the Wikipedia language, that's quite a structured data. You can see this. This was born, right? So the birth date can be extracted to relationship was born, and extract data by regular expression. It can also extract the actual time, then you can create the knowledge was born Jim Gray 1944 1 at 12, right? So this is then you can put it inside your database by just processing the Wikipedia. So if you go further, you can find attribute value in the full text. James Jim Gray, right? So basically, if you create a pattern, born, month, day, year, then you can apply this pattern in somebody else. Rugo were born April 31, 1965. If you apply this pattern, you can see that you can actually fulfill the data. Sorry, you can upload and fulfill the data inside his profile that you don't have yet, right? So it's born on date, Rugwell 1965 or 431. You can have somehow factual knowledge. You can have a pattern-based harvesting. You have facts candidates and patterns. Jim Gary, Mike Harrison, and Barbara Liskov, John McCarran. And then the patterns can be X and his advisor of Y, X under the guidance of Y, right? So then you can get more patterns, more entities with this kind of relationships. So Jeff, Alan Jeff, Sonita Mike, and Renee Yanis. And from there you can get patterns that X and Y in their paper, like basically they were inside the co-authors in the paper, or they co-authored the paper, or they were mentioned in the same paper, or rarely met his advisor Y, right? So then from there you can enhance the facts and fact candidates more, and then you can find the new patterns appear. So this is like a continuous process. Yeah, so facts yield patterns, and then patterns yield facts, and facts yield patterns yield facts. So is how you can grow this knowledge structure. So it's good for recall, but it's very noisy and not robust enough for high precision, right? So sometimes this process gets uncontrollable, you might get quite low precision. So they can be formulated statistically how you want to assess the patterns. I probably won't go too much into this slide, but just you can see that supported of pattern can be calculated number of occurrences of pattern with the seeds E1 and 2, and occurrences of pattern divided by occurrence of all patterns with seeds, right? So it's called support of the pattern. And then confidence of pattern of occurrence of pattern with seeds with E1, 2, so the same top part, and then it's basically divided by number of occurrences. So confidence of fact candidates can be defined based on the formula below, right? So we can iterate this process and can promote best facts to additional seeds for next round, right? So basically, it's an iterative process of scoring different patterns and choosing which patterns have a good chance to be in a knowledge graph, or which one cannot be having a good chance in a knowledge graph. If you want to put some negative seeds, right, for the patterns, that actually can increase the precision. It's pretty much like negative sampling in machine learning here as well, right? So if you have positives like truth positive seeds is one information, but if you have a more negative seeds that, like say Sydney, Australia, Istanbul, Turkey, right? Then that would help you to get the better idea of getting a more robust system that can infer these patterns confidently and robust. So again, we can compute confidence of pattern as in a formula and can promote best facts in the additional seeds for next round. We can promote rejected facts into additional counter seeds, right? So that works more robustly with a few seeds and counter seeds, right? So basically, this tells you that this is pretty much like a negative sampling in machine learning and helps. So basically, we need not just positive knowledge, but also negative knowledge. So some patterns are too narrow and they have a small recall, so it's hard to find them. For example, X and his celebrated advisor Y, right? Or X received his PhD degree in the CS department at Y, right? So it's very, very narrow. Or X obtained PhD degree in the maths at Y. So we can generalize pattern as well. So to make this happen more common, it's the same way as we have n-grams and bag of words, right? N-grams are less common. Bag of words, which is 1 grams, are more common. So you can generalize pattern that X has a doctoral research or under supervision of Y, or X very good advisor or be a doctoral research that supervision of Y. Yeah, so compute n-gram sets by frequent sequence mining, and then after that you can compute some match of quality pattern with sentence Q by Jacquard similarity. In this way, you can cover much more sentences, and that will help you to increase your recall and makes your system works better. All these papers, by the way, you can find in a Google Scholar, and then you can read these techniques a little bit more in more details. So you can also do deep parsing. So the problem they try to solve is surface patterns fail to if the text shows too much variations. But for example, Cologne lies in the banks of the Rhine, right? Paris, the French capital, lies on the beautiful banks of the Seine, right? So sometimes there's more words inside, so we want to have linked relationships across some words that are inside, not just direct relationship inside there. So sometimes we want to have deep linguistic patterns that long relationship, short next one, and long relationship, and shorter and shorter relationship. Something like this. So it's not immediate hope inside the graph and the sentence, but it's more like more distance keywords happening together. And of course, we have so-called web table methods, and these web tables provide us some relationship information. Basically, this is quite easy to mine because we already have categories. We can just parse these tables and get lots of knowledge by getting this information from these tables. So web tables can be annotated with Yago, and the goal here is enable semantic search over web tables. So the idea is map column heads to Yago classes and map cell values to Yago entities, and then using joint inference factor graph learning model. So examples would be have a title, Hedges guide, and then also the items, and then you can have a short history of time and as Hopkins, and then you can take a book, you can take a person, and then in Yago it also has author relationships coming out of that. So book has a title, author is a person, correct? And then therefore we can create a relationship inside based on this information from web table has author because Yago has the relationship between book and person, and that's because they are both entities. So this is how it works. We can also infer classes from occurrences and headers that's of a class name. So for example, we have a header once and we have another header too. So if they often co-occur at the same time, then you can create a relationship between them as a common couple. Yeah, so it's like a statistical approach. Temporal knowledge harvesting. So for temporal knowledge is crucial for machine learning news, social media, and opinion. So basically, temporal knowledge is pretty much everything related to time. So if you combine linguistic, statistic, and logical reasoning, it's harder for us to handle this temporal knowledge rather than ordinary relationship is basically the same. Is basically the same occurrence, the same type of knowledge. So so we have some web content, we still have some knowledge. We can have intelligent interpretation of web content, and we have knowledge acquisition inside there, and then then this universes continuously interact between each other to get better performance in the end. So to summarize, knowledge bases from web are real big and very useful. We have entities, classes, relationships. The key assets of this whole universe is, of course, intelligent applications. Semantic search, question answer, machine reading, digital humanities, text data analysis, summarization, reasoning, smart recommendations. And as well as we can combine harvesting methods and methods of inferring knowledge out of there, we can extract some relationship facts. And then based on these data banks that we build automatically, we can solve loads of applications in search, in a question answer, and many, many other things. And you can see that key vendors, key technological vendors nowadays, like Google, like Facebook, they all have their own knowledge graphs built. The issues you can find is creation of initial knowledge graph, populating of instances inside, like we have seen with WordNet and Wikipedia. Analysis of latest social web info, so basically population and update of knowledge graph, and adding new instances inside, as well as combining knowledge graphs one to another. You can also look for vertical domains. So basically, in particular domains, knowledge graphs also can be applied, and it can be used in knowledge inference and trial of question answering. Yeah. So basically, the last thing means that if you have some very narrow domain, you can actually build knowledge graph that will be helping you to establish recommender system and really answer your questions. So thanks for joining us today. Sorry again for some interruption and noise. I hope you enjoyed, and I guess next week we'll get next lecture, so additional lecture on computational advertising. Plus, we'll have our tutorial. Have a good day. Bye.